Okay, good evening to Dr. Su. So today, me and Rahmah will be presenting our assignment 2 on advanced reinforced concrete design. Okay. Okay, so here's the first question where it asks to design the reinforcement for both beam and column according to your code 2. Okay. And first, we are going to determine the reinforcement for beam. Okay, here's our all the data given. Okay, first, the first analysis that we're going to do is determine the self-weight for beam and slab to be substituted into the equation for the permanent action to obtain the design action. So the beam self-weight we obtain here is 3.5 kilonewton per meter, whereas for the slab self-weight is 36.25 kilonewton per meter. And here's the characteristic variable action where QK is equal to variable action multiplied with the length of the slab divided by 2, and here we get the QK is equal to 50 kilonewton per meter, whereas the permanent action that have been said earlier that it is the total of the self-weight for beam and slab, and here it is equivalent to 39.75 kilonewton per meter. So using the given load factors in the question, we obtain the design action equal to 128.66 kilonewton per meter. And here's the UDL, where the shear force is equal to WL, the length of the beam, divided by 2, and equivalent to 450.32 kilonewton, whereas the bending moment of the beam is equal to 788.1 kilonewton meter using the formula of WL square divided by 8. And here's the highlighted part where we need to determine the main reinforcement for the beam, where first we need to determine the effective depth. And here's the formula given where the effective depth D is equal to 617 millimeter, whereas the D prime is equal to 73 millimeter. And here's the ultimate moment using the formula equal to 0.168 multiply with the concrete strength, multiply with the width of the beam, and then multiply with the effective depth power square power 2. And the ultimate moment is equal to 716.3 kilonewton meter. And based on the condition here, the design ultimate moment is more than the bending moment of the beam. So the compression is required. So first we need to determine the K value, where K value is equal to 0.185 through the formula. And based on the condition here, the K value is more than the K balance. So we are going to substitute K balance equal to 0.167 into the formula of Z to determine the lever arm. And here we obtain the Z equal to 506.34 millimeter. And here again, the condition is that we need to choose the lever arm that is less than the 0.95D. So here we are using the lever arm to determine the X value, and the X value is equal to 276.64 millimeter. And we are using the X value to determine which formula we are going to use for the area required for compression reinforcement. And so the D prime is equal D prime divided by X is equal to 0.264, and since it is less than 0.38, so we are using the above calculation to determine the area required for compression reinforcement. So the required area is equal to 322.99 millimeter square. So based on the table, we are going to compare the calculated area using the table. So we're going to choose the area that is more than the calculated required area. So based on the table here, we're going to use 3H 2H32 is equal to 1610 square, since it is more appropriate. And here, we proceed to the tension reinforcement calculation, where the formula is given here. That is, area required for tension reinforcement is equal to K balance multiplied with the FCK multiplied with the width of the beam multiplied with the effective depth power 2 divided with 0.87 multiplied with the FYK multiplied with the Z, and then plus with the required area from compression and multiply with the FSC divided by 0.87 times FYK, and the required area for tension is equal to 3,553.84 millimeters square. And so we are going to compare with the sectional area table, and here we can obtain the area. We can use the 5H32 for our design because the area is more than the calculated required area. And we proceed with the minimum and maximum reinforcement area calculation, where the FCTM we can obtain through the interpolation from table 3.1 in area code 2, and it is equal to 3.05 Newton per millimeter square. And we substitute the value into the area required for minimum area required for secondary reinforcement, and it is equivalent to 342.5 millimeter square. And here again, we are going to choose the greater value for the minimum area, and we can conclude here that the minimum area is equal to 342.5 millimeter square. And lastly, for the maximum area required, it is equal to 0.04 multiplied with the area of the beam, and as you can see here, the maximum area required is equal to 9,660 millimeter square. And here's the conclusion for the design that we've obtained for the beam. Okay, so we're going to proceed for the column section, okay, of the same question. So here are the given data. Okay. Okay, so for the column reinforcement, we need to determine the clear height of the column. Okay, so based on the calculation, the clear height of the column is equal to 2510 mm, and to determine the effective length of the column, we first need to determine the moment of inertia. So here are all the data given for moment of inertia for both column and beam, and also the stiffness. Okay. So here is the calculation for the relative column stiffness, where the top end and the bottom end for both Z and Y axis are being chosen when the value are greater from the comparison. Okay. And so here's the effective length of column by using the simplified method. Okay, that is it is equal to the factor that we can obtain from the table multiply with the length. And since the end condition at Z exists for both top and bottom is equal to 1, so from the table we can obtain the factor is equal to 0.75, and it is the same goes to the end condition at y-axis. So in a conclusion, the effective length of column is equal to 1883 millimeter. So after we determine both the clear height and effective length of column, so we're going to determine the design moment. Okay, so we are going to first calculate the eccentricity, where these are the condition, that is eccentricity is equal to L naught divided by 400, or h divided by 30, or equal to 20 mm. And the 20 mm we obtain from the Eurocode 2, and based on this we are going to choose the eccentricity that are maximum numbers between those three. So 20 mm is the maximum number for the eccentricity. So we're going to substitute the eccentricity value that is equal to 20 mm into the calculation of M02 is equal to bending moment plus with the axial load multiplied with the eccentricity. So the M02 is equal to 150 kilonewton meter, whereas the minimum bending moment is equal to 50 kilonewton meters. So we're going to choose the maximum number between those two, where the design moment is equal to 150 kilonewton meter. And here's the reinforcement calculation, where D2 is equal to nominal cover plus with the diameter of the ties plus with the diameter of the bar divided by 2, and D2 is equal to 65.5 millimeter. And using this calculation, we are going to determine the AS using this figure. Okay, where through the interpolation we can obtain the value equal to 0.28. So we are using this calculation to obtain the AS that is equal to 2509 mm square. So again, using this table, we're going to choose area that is more than the calculated area. So from here, we are choosing 6H25 as our selected design for column. And here's the calculation for minimum area required and minimum area required, where it is equal to 575 millimeters square, or we can use the formula of 0.002 multiplied with the area of the column equal to 2 at 0 mm square. And here's the maximum area required equal to 5,600 mm square. And whereas here is the link, the calculation for the link, okay, from the Eurocode 2 clause 9.5.3, okay, we can obtain the formula where quarter of the diameter of the bar is equal to the diameter of the minimum link is equal to 6 mm, and we're choosing the maximum, okay, as our selected diameter for the link, and here we can assume that our selected diameter for the link is at mm. So again, here's the calculation for the space, and here's the calculation for our SCL is equal to 20 multiplied with the diameter of the bar, and we can obtain the value is equal to 500 mm, and we are choosing the minimum value between the calculated SCL with the width of the column, or 400 mm. 400 mm is given in the Eurocode 2 clause 9.5.3, and so here in the conclusion we are using SCL max is equal to 350 mm. So using the hash add and 350 mm, and at section 300 mm below and above beam and atlet joints, SCL max is equal to CL max using the factor 0.6, and here we can obtain it is equal to 210 mm, and using the H at 210. 。
Okay, then we move on to the next problem. So given the details of the office building as shown in the screen, so for the calculation, we need to identify the design of the structure for continuous beam 1A, A to B. And we have to, from the section, we have to calculate the total load. So the self load equals to 2.75. Then from the formula, we can get our total load equals to 10.24 kilonewton per meter square. For the moment diagram as shown here, then for the total load, we can get the value as 81.92 kilonewton. So for the next step, we need to design the main reinforcement. So for span AB and CD, the value of D is equal to 452. And then from the table in Euro code, we can get the moment as 58.98 kilonewton per meter. And then also the moment, limiting moment, which is equal to 4,295 kilonewton per meter. So since the value of moment is less than the limiting moment, compression reinforcement is not required. So next we have to get the value of stiffness K, which is equal to 0.0038, and then the value of lever arm Z is equal to 450.48. Then we can find the value of AS required, area required, which is equal to 300.98 millimeter square. And then from the table A.2 Euro code, we can get the rebar details as 2H20, which giving the area provided as 628 millimeter square. So then for the span BC, the same steps as the previous calculation, you can get the value moment as 429. Throughout the calculation, you can get the area required as 233.96 millimeter square. And then from the table, you can use this 2-20, with having the area provided as 6 millimeter square. So the next step is to get the shear reinforcement. So we assume the spacing of the shear links will be 150 millimeter. So from the equation, we can get our value for area minimum is to be 11.99 millimeter square. And then from the equation Eurocode 9.12m, the value for AC is 5,995 millimeter square. Also, we can have our value of AS maximum as 239.8 millimeter square. So from the table in Eurocode, the bundling should be 4HF, with giving the area provided as 201 millimeter square. So to get the spacing calculation, so using the formula, we can get the spacing as 160 mm. So for this design, the bar will be 250 mm.
So here's the problem number 3, where the problem asks us to calculate the slenderness of column and classify the column whether it is slender or non-slender. Okay. Okay, so here are all the data that been given from the question. And here's the dimension dimension for the structures where the column at Z axis, the length of the column at Z axis is equal to 4,500 mm, and the Y axis is equal to 4,600 mm, whereas here's the dimension of the length for the main beam, okay, and the secondary beam. Okay, here's the amount of inertia calculation, whereas for the z-axis, for the column is equal to 9.83 multiply with 10 power 8 mm4, whereas the moment of inertia for column at the y-axis equal to 607 times 10 power 8 mm4. And here's the moment of inertia for main beam that is equal to 2.6 times 10 power 9 mm4. And here's the secondary beam moment of inertia that is equivalent to 1.33 times 10 power 9 mm4. Okay, so we're moving to the stiffness calculation where the formula is equal to EI divided by L. Since the EI is assumed as a one component, so here I just substitute the formula as I is equal to divided by L. Okay, and here we can, okay, here we proceed to the relative column stiffness calculation at z-axis, okay, where it is equal to the column stiffness at z-axis divided by 2 multiply with the total column stiffness at the both beam, okay, and it is equal to K2 is equal to 0.14, and here's the condition. We are choosing the number that is greater than the comparison given. Okay, same as the bottom end. Okay, we're choosing the K1 is equal to 0.14. Okay, and here's the effective length of column calculation at z-axis. Okay, where we obtain the formula from the record 2 in clause 5.8.3.2, it is equal to 2,795 mm. Okay, and here's the relative column stiffness calculation at y-axis. Okay, and we're obtaining the values same as the formula we have obtained the relative column stiffness at z-axis. Okay, and here we proceed to the effective length of column calculation at y-axis where it is equivalent to 2,718 mm. Okay, so for the radius of gyration calculation, at z-axis, it is equal to square root of the moment of inertia at z-axis is divided by the area of the column, and where it is equal to 101 mm. As for y-axis, it is equal to 79.4 mm. And we proceed to the slenderness ratio calculation for both the axes, where for the z-axis equal to 27.7 and y-axis is equal to 34.2. And as for the slenderness limit calculation, here we are making an assumption where the axial load is equal to 1050 kilonewton. And as for the major axis at the bottom end, it is equal to 12 kilonewton meter, whereas at the top end, it is equal to 40 kilonewton meter. And as for the main axis, for the y-axis, the bottom end is equal to 10 kilonewton meter, whereas the top end is equal to 15 kilonewton meter. So we proceed to the cylinders limit, and before we calculate the slenderness limit ratio for the column, we need to obtain this component that is a, b, c, and the square root of n. So here, the condition given where a is equal to 0.7 since the effective is unknown. Okay, same goes to b is equal to 1.1. Okay, whereas the C is equal to 1.7 minus the moment ratio. And here, from the assumption that we've made towards the major and main axis for the moment, we'll substitute the values into this formula. Okay, so the moment ratio at z-axis equal to negative 0.3. So whereas the moment ratio at y-axis is equal to negative 0.67. So we're substitute both the values into the respective calculation to obtain the c values for both the axes. Okay. So the z-axis, the c value is equal to 2, whereas the y-axis c value is equal to 2.37. And here we're going to determine the n value, where it is equal to axial load divided by area of column multiplied with the FCD, and the FCD is equal to 0.85 multiplied with the FCK divided by 1.5, and here we obtain the FCD value is equal to 14.17 Newton per millimeter square. And with all the measured value, we substitute it inside this formula of the slenderness limit at z-axis, and it is equal to 35.1. And based on this condition, if the slenderness limit is more than the slenderness ratio at z-axis, then the column is considered as non-slender. And the slenderness limit at the y-axis equal to 41.5, and it is more than the slenderness ratio at y-axis. So we can conclude that it is considered as non-slender column. Okay. And here's the alternative method to determine the classification of the column. Okay, so here the end condition as it exists is equal to 1 both at the top and bottom end, and the factor is equal to 0.75. So the factor is multiplied with the length at the respective axis. So for the z-axis, the length is equal to 3,375 millimeter, and as for the y-axis, the effective length is equal to 3,450 millimeter. So using the effective length, we are using it to determine the slenderness ratio, and here at the z-axis is equal to 30.4, and it is less than the calculated slenderness limit ratio. Okay, so we consider it as non-slender, whereas the slenderness ratio at the y-axis, it is equal to 43.5, and it is more than the slenderness limit ratio at y-axis. So we're considering the column at y-axis is equal to a slender column.
Okay, we move on to problem number 4. We need to determine the actual force of bending moment of problem 3. So the force and bending moment in the column B2. The details of the beam are shown here, and also the previous figure on problem 3. After identify. So firstly, we have to get the actual force, the total design load, which is from the table. From the table, data is given here for beam 2 AC and also beam 3 1 to 4. So from the roof to the first floor, our load is equal to 313.6 kilonewton. And then from the first floor to the ground floor, load rolling is 4979 kilonewton. And ground floor to the footprint, 512 into 8 kilonewton. So altogether, for the total load is 122.03 kilonewton. Other than we have to calculate the bending moment. So formula for stiffness is K equals to BH power of 3 over 12. So we can get the stiffness value for each column, which is the column is 4 meter, 5 meter, and the last column is 1.5 meter. And then also for stiffness for the beam 4 meter, and also for the beam the second 4 meter, AB and BC equals to 0.33 and 0.2. Okay, to get the moment in column D2 from the roof, you can use the calculation for moment, and then you can get the final value as 30.2 divided by 20, which is the lower column. And when at the first floor, our moment is equal to moment for the lower column, the 5 meter column equals to 40.03 kilometer meter, and the moment for upper column 4 meter is equal to 40.96. Okay, at ground floor, our moment will be for column lower column 1.5 meter is equal to 49.14 meter. For the upper column 5 meter, our moment D2 is equal to 4.96 kilometer. So also we have to identify our second moment order, which is equal to 24.5 kilometer. So on the diagram, we can have our bending moment diagram from the upper column on the roof, first floor and the ground floor, upper and lower column. Okay, that's all.
So here's the final problems in the assignment. Okay, where it asks to design the flexure for the column. Okay. And here's are all the data that been given inside the question. And here's the durability, bond, and fire resistance calculation, where the C deviation is equal to 10 mm, and the minimum cover with regard to bond is equal to 20 mm based on the given diameter of the bar, and the minimum cover with regard to durability is equal to 35 mm. So here to determine the minimum required exit distance with regard to environmental condition, we first need to determine the NV that is equal to 0.7. Okay, which is the recommended value given inside the record 2 part 2. And here's from the calculation here we can obtain the 36 mm from table 5.2a inside the record 2 part 2. Okay, and here's the calculation for the minimum cover that is equal to A minus the diameter of the limb minus the diameter of the bar divided by 2, and we get the C min is equal to 30 mm, and the C min is chosen based on the maximum number on those three C min. Okay, so the nominal cover is equal to the selected C min plus with the C deviation, and the nominal cover is equal to 35 mm. And here the design moment calculation, where first we need to determine the eccentricity. Okay, so the EI is equal to L0 divided by 400 and equal to 9.5 mm, and then E naught is equal to H divided by 30 equal to 10 mm. Okay, and here's the condition. Okay, E not is chosen is chosen based on the greater number. Okay, and here it is chosen as the 20 mm since it is greater than the calculated E naught. Okay, so the moment is equal to maximum moment between the bottom and the top moment that's been given inside the question. So the M is equal to 35 kilonewton meter, and the MO2 is equal to moment plus with the axial load multiplied with the eccentricity equal to 46.4 kilonewton meter, and then the minimum bending is equal to axial load multiplied with the E naught and equivalent to 24 kilonewton meter, and the design moment is equal to the maximum number between the M minimum and the M02, and it is equal to 46.4 kilonewton meter. And here's the reinforcement calculation where D2 is equal to nominal cover plus with diameter link plus with the diameter bar divided by 2 and is equal to 51 millimeter. And here again, we need to determine all of these three. Okay, from this calculation, that is 0.2, 0.64, and 0.08, we can use the figure 8. We can use the design chart to determine the AS, where using the interpolation, it is given here that the value obtained is 0.35. Okay. Okay, and the area required is equal to 1,313 millimeters square. So, referring to the sectional area of group of bars table, we can obtain that the applicable area is equal to 1,260 mm square. That is, that is referred to 4H20. So we're going to use that one for our design. Okay. And here we are determining the minimum area. Okay, that is equal to 0.10 multiplied with the axial load divided with the FYD, and the FYD is equal to 0.87 multiplied with the FYK, that is equivalent to 435 Newton per millimeter square. So the AS mean using this formula, we're obtaining value of 276 millimeter square, and also we can use formula of 0.002 multiplied with the area of column to determine the AS mean, and it is equivalent to 150 mm square. Okay, and here's the formula to determine the maximum area, that is 0.04 multiplied with the area of column equal to 3000 mm square. Okay, and then here is the calculation for the length of the column, where we are going to apply for our design that have the greater value when comparing with the diameter of the minimum link and the diameter of the link. And since the diameter of the link uh, is since the calculated diameter link is 6 mm, so we're using that value for our link, and whereas for the spacing, we are using 250 mm since it has the minimum value when comparing with the calculated spacing and the 400 mm. And we are using H6250, and as for at section 300 mm below and above beam at lap joints, the maximum spacing is equal to calculated maximum spacing factor by the 0.6 and is equal to 150 mm. So we're using H6150 for our design. Okay, thank you, and that's all for our discussion.
Okay, thank you.